Hi, welcome to the Signal Path. In this episode, I have another product repair for you guys. This is an Agilent Technologies E8267D, which is a PSG vector signal generator. These are the highest end vector signal generators that Keysight or Agilent has, and I think they go up to 44 gigahertz. This is a 20 gigahertz version, and it doesn't work. And this was provided again by AllTest for us to play around with. AllTest has such a huge inventory of components and equipment that I can pretty much ask for anything, and they'll have both broken versions like this one and fully functional ones with warranty and calibration, of course, which you can purchase. They also recently launched AllTest Chambers, which is an environmental testing facility where they can stress test various products under snow, humidity, moisture, temperature, and so on. That's a new line of their services that they're offering. I have the links for all of that in the description in case that's something you want to pursue and check out for yourself. Now, this particular unit, as I said, it is a very high-end instrument precisely because it has the vector signal modulation capability with wideband inputs at the back. And if you buy the really high-end version of this, I'm not sure if this one has it, it will even have a built-in arbitrary waveform generator on I and Q channels independently. So you can create pretty much any modulation you want up to 44 gigahertz. I don't think the 67 gigahertz version of these instruments has that capability yet. I haven't checked recently, but it's something worth looking at as well. So this one doesn't work. We don't know what's wrong with it. Let's turn it on and give it some tests. All right, the CAT scan is also ready to go. So now we're going to test this instrument using the Signal Hound SM200C, and this is a 20 gigahertz instrument. That's a 20 gigahertz synthesizer, seems like a good match here. And this allows us to also look at any kind of fast events that happen because it has real-time 160 megahertz IQ streaming over fiber optics, which I've done a full review on Teardown as well, so you can check that out. So I already turned this on actually before, and I didn't see any problems with the boot up. It boots up perfectly fine, doesn't report any particular errors, which is interesting. And then we're going to take a look and see what comes out of the front end of the instrument. This is a very basic setup right now. Okay, let's give this a try. So at the bottom right, you can see the screen of the synthesizer, and of course the GUI of our Signal Hound, and I have already reduced the resolution bandwidth to about 30 kilohertz, so we can see a little bit more of the noise floor. So let's change some of the settings here. Now, first thing to notice is that if I go under utility and under error info, there's actually no errors at all in the queue. So that it's not generating anything. Even in power on, it doesn't generate any errors. That's interesting. So let's set the frequency to very low, and we can start from 100 megahertz. That puts it in a very particular part of the synthesizer operation. We'll take a look at the block diagrams. Turn the modulation off. Set the amplitude here to 0 dBm. You can hear the relay clicking, and turn the RF on, and wow, nothing at all. But it's also interesting again that there is no error. This is very helpful actually, because there are not that many places where there can be an absence of an RF signal and you get no errors. And that's because there are a lot of ALC loops, synthesizer loops inside this instrument, which will generate an error if there is a problem with it. So not seeing anything at this point and not seeing an error actually means that the problem probably confined to a very specific area of the instrument. And we'll talk about that too. So let's go from 100 megahertz. Let's just keep increasing the frequency at 0 dBm and see what we get. 200, 300. Nope, absolutely nothing. Here's 1 gigahertz. And we can go up 1 gigahertz at a time. Here's 6 gigahertz. Still, I see nothing at this. Oh, there it is. Look at that. There's a tiny, tiny little frequency there. What is that frequency here? Tiny little signal. Yeah, this might actually be the right frequency. The signal is tiny though. It's like minus 90 dBm. Wow, that's 90 dB below where it should be. There's 10 gigahertz. There you go. There it is. It's moving around. Oh, it disappeared. There we go. Here's at 15 gigahertz and 0 dBm. And yeah, indeed, we can see from the instrument we are getting exactly 15 gigahertz. If I can move this mouse, there's 15 gigahertz minus 88 dBm. Yeah, we're way, way down where we should be. So let's continue. 16, 17, 18, 19, and 20. So the highest frequency is actually generating at 20 gigahertz. Let's go back to 15. And let's change the amplitude. Again, still no errors anywhere to be seen. Go up by 1 dB. Oh, look at that. It does go up. I just heard that attenuator click. Yeah, it's still doing it. What am I at now? 15 dBm. Got to be a bit careful here. 20 dBm. If there is an attenuator problem, let's say, and you keep increasing the frequency, increasing the power, and the attenuator works in some ranges, you could all of a sudden hit a huge power into your device and destroy the device. In this case, the Signal Hound plus 20 dBm is the maximum input, so I'm not going to go over 20 just in case. Let's go back down to, let's say, 10 dBm, which is safe. Change the frequency. There it is. Look at that. That's interesting. Look at it. Between two frequencies, all of a sudden there is nothing. That's strange. So here's a service manual of this instrument, and it's 417 pages. Nobody in the industry makes service manuals as good as Agilent and Keysight. Unfortunately, this is also a downhill trend because they want to protect their IP for various reasons. It's a very complicated situation, but it's unfortunate because there's so much to learn, and of course these things saves the instruments and save the customers money at the end of the day for not having to send the instrument in for repairs that could be trivial. So here we go. This is a lot of stuff going on here. So here's our main YIG driver, and there's a fractional N, which is the fine-tune portion. Here's the output section. So we want to look at for the output connector somewhere on this big mess over here. And here it is. Here's our RF connector right over here. So you can see that this section here, which is the main output, also can have multiple different models. Depending on which model you're using, you're going to have whether there's additional multipliers or filters or not. But take a look at this. Right at the RF connector, we have the attenuator, AT1 attenuator section, which is controlled by the attenuator control signal circuitry bus, which is part of the digital bus on the motherboard. But then right before it, we have the detector, which operates from 2 to 20 gigahertz, and below 20 gigahertz, there's a separate detector path. But if you look at this detector output, it comes over here and goes into this ALC circuit to do amplitude leveling. If this detector doesn't detect enough signal, you will get ALC error. It will tell you that the instrument is not able to hit the power level it is supposed to hit because it notices that this loop has been saturated. So if the instrument is not generating that error at all, a good place to look is in this attenuator. That could be the reason why there is nothing coming out. You may hear the attenuator click back and forth because these are electromechanical, but the connection to the output could be completely broken. So in that case, you have to change the attenuator or repair it. I've done that before as well, but nonetheless, we're going to try it again here. But we have to make sure. And the way to make sure is to sever this connection right here, connect this portion to your spectrum analyzer with the appropriate, of course, attenuator in the way so you don't damage anything, and see if this is, nice and uniform. It has the amplitude you expect across the entire band, and then you can measure the attenuator separately. So I suggest that's where we start. And then if necessary, if there's something else wrong, we can go over, take a look at this entire LC loop and see if there is any other problem. It is possible that the instrument is not meeting amplitude because the LC is broken and the error is not showing up because that part of the circuit is also actually broken. But anyway, I think that's more unlikely. Here's another section of the circuit which is very interesting, which I like to try out, and this is the IQ modulator, which works in this case up to 20 gigahertz. And you can even have that higher frequencies. And you can see here we have the IQ modulator with various analog bypass paths coming in. This analog bypass path, I think, that's just a normal path going forward. Where's the signal coming from, the IQ? It must be coming from the baseband generator. Yeah, it's coming from all the way over here. That's right, the analog and modulation generator. But there is a override of this where you can inject your own IQ signal directly into the modulator, and then you can create, very complex modulation higher than the bandwidth of the instrument. So I like to try that too. But one step at a time. Time to take it apart and take a look inside. And here's inside the instrument from the top, and as soon as I opened it, I found several things I wasn't expecting. First of all, this screw fell out, which is unfortunate because I don't know where it came from. And the back of this, on the other side of this instrument, the entire motherboard is exposed. So having loose screws in there is really a bad thing. So luckily, we found this one. And then from left to right here, various boards. We have the sampler board, the fractional N, the reference, the low band output, the YIG driver. Then we have the ALC. Yep, that's the ALC. Modulation generator of some kind. We have the low band switch filter. Then we have the baseband IQ generator and these high density ribbon cables going to the back. And that's because this one actually has a digital IQ output as well, which is quite nice. At the far back, we have the oven controlled crystal oscillator, quite large for this instrument because it does require a very, very good 10 megahertz reference. And then the fan and everything is there. But take a look at this. Look at what's going on over here. Now that's interesting, and this tells us that someone's definitely been in here before. The attenuator isn't even connected to the output. This is the signal going into the attenuator. On the other side, it goes to the front connector. Yeah, so this is not there, which means that somebody else probably already figured out that that's the problem, and they, for some reason, either didn't repair it or just left it as it was. This cable is actually completely loose from here, so it can be disconnected. Another thing that's interesting to note is that the final ALC that I just talked about on the block diagram is implemented using off-the-shelf components. So we have a coupler over here, the signal goes in, couples portion of it to this side and then straight through, and that's how it was drawn in the block diagram too. And there's a section over here with a detector at the end which detects that, and so that this is part of the ALC loop, and that goes into the board over here to close that. This little tiny board over here, that's an add-on, looks like something they figured out they needed to do afterwards. Not quite sure. It does look like it's a weird addition, but this is a detector bias on the high band. I don't think it's this detector because that's coming from here. It must be another detector on the board that's just attached to it. So yeah, bit surprised. This could still mean that this is broken. So the signal we were seeing was just a leakage of this floating around and just coupling into the various nodes. That's how hard it is to get isolation. Hopefully they give you some appreciation of just this signal sitting over here can still give you that kind of signal that you see at the output. Well, I think we should still do the same thing we were going to do before. Remove this here, take a look at the signal and see its performance. And we can also look at the other side of the instrument and see how complicated it looks. So another quick thing to notice over here, I removed the cable that connects the attenuator to the coupler, and if you look at this, you can see on one side this is an SMA cable, and on the other side is actually a 1.8 millimeter connector. Oop, if I can get it into the picture, there it is, 1.8 millimeter, which means that this guy is a 1.8 millimeter connector as well. That means this attenuator is probably rated to 50 or 67 gigahertz. So they're using the same front-end attenuator for all the higher-end models of this instrument. So this is a really expensive part, unfortunately, even though everything below this is rated to 20 gigahertz only, but they've kept this front-end very expensive. That makes this even more interesting to try and take a look when we open it. But nonetheless, I think the first test of checking this is the most important. Alright, so here's our modified setup, nothing unusual. We have a direct connection with the 20 dB attenuator to the input of the spectrum analyzer so we can see if there's anything coming out. Okay, so let's give this a try. The error that you see on the screen here, oven cold, over here, that's normal. That's just sitting there because I restarted the instrument and it's cooled down. So we're at 1 gigahertz 0 dBm. I'm going to turn the output on and check it out. There it is. That's not bad. Remember, there's a 20 dB attenuator in the way. So it's actually producing about 5 dBm, which is correct. You can go down below 5 dBm using some of the electronic and mechanical attenuators combined, and above that is the amplifier inside the instrument that takes care of it. Let's go ahead and try the higher frequencies. Again, I don't suspect any problem, just for the sake of completeness here. 1 gigahertz. Here's 2, 3, 4, 5, and we can continue on. There's going to be some drop. That's the cable losses. There you go. Looks good. And I can do now half a gigahertz at a time. Fill in some of the blanks just to make sure again, and yep, no problem at all. So I went ahead and reconnected the internal attenuator back and removed the external one. So now we can see what the actual built-in attenuator was doing before under the same conditions. So here's the output. Interesting. So it is actually producing something. So it's definitely one of the attenuator stages that's broken. Let me do a peak tracking on this again. There you go, minus 30. So instead of 5 that it was reading before, so there should be some attenuator in there, it should be reading 0, it's reading minus 30. So that's an interesting point. Let's go ahead and change the actual power. If I go up and down by a few, there you go, attenuator switched. Yeah, it's producing, that's a lot of power now because it's trying to produce 19 dBm. Of course, it's not able to. We go down. Oh, this is now on hold. I'm going to go and change that to clear right so we can see minus 27. I'll continue going down. There you go. Attenuator clicked, click, click, and click. Okay, so it's actually doing pretty good. Yeah, it's doing well. That means only one of the stages of attenuation is actually broken, but it seems to be permanently engaged on one of the attenuation stages. Okay, that's not bad. So we're going to take the attenuator out of the circuit now so we can take a look at it separately by itself. And here's the back of the instrument, and on the top left over there you can see the attenuator right there. Here's the control that goes into the attenuator control section. There's all the other various LO generation synthesizer blocks and so on. These are the different cards on the other side. Look at how much DC-DC conversion, frequency, and filtering is going on over here. This is intended to be easily removable, so I'm going to do that, and we can measure it separately. So we can of course test the attenuator using the instrument itself because it provides the control circuitry to switch between different attenuation stages. This has several stages in it, with the smallest step being 5 dB and then 10 and I think 20, then 240 dB stages in there for a total of 115 maximum. So this means that we can use this, and I just realized that this is ridiculously hot. It's actually too hot to touch. I think this is the heatsink for the YIC controller. Wow, I didn't realize it would get this hot. Anyway, so it's connected. So right now the attenuator is set to the maximum value, so it's well beyond the dynamic range of this network analyzer, so we can't see anything. But I've put some markers so we can read the value. You're looking at this value over here. Maybe it just makes more sense for me to actually zoom in there. So I'm going to put these to 10 dBm, but I don't even need to enable the output for that. And it should give us the minimum attenuation, which should be essentially 0. What do we have? There you go, minus 0.7. That seems correct. We're measuring this at 5 gigahertz. So that's right. So what is the issue then? Okay, let me reduce the power. We should see 5 dB at a time. Here's the first one. Yeah, that's 5 dB. Perfect. That's another 5. 15. 20. Well, it's fine. What is going on here? 25. 30. 35. 40. No, there's nothing wrong. That's really strange. So I think by now we've pretty much used all the stages except maybe the last 40 dB stage. That is really odd. There you go, 85, and maybe we can hit 90. Yeah, there's 90. I don't understand. The attenuator is working. Okay, let's turn into a bigger puzzle. Well, there's really not much else left. I mean, there's the two cables, the coaxial cables that connect the front end of the instrument to the attenuator, and then from the attenuator back onto the coupler. So we should measure those as well, just in case. The other thing that I worry about is that, as you know, these are electromechanical devices, and maybe one of the stages was stuck, and by moving it and putting it around, maybe I kind of released that stuck and it's now unstuck, so it's working again. That would be really frustrating if that's the problem. But anyway, let's try the other cables. Okay, so here's the cable connecting the coupler to the attenuator, and it measures fine. You can see it's quite flat, and we have about half a dB of loss. That's probably most of the loss of this front end is probably from this cable. So this is looking good. Now there's one other one. Okay, so here's the cable that connects from the bottom of the attenuator to the front of the instrument. You're not going to believe it. It's broken. That's the problem. It has 20 dB of loss, which is roughly what we were seeing. Of course, it's going to be a function of frequency. You can see how it goes. The loss gets better with frequency because it's just a capacitively coupled node now. I can't believe it. That's not what I was expecting at all. Well, it's also actually quite a bit better because this is a much cheaper thing to replace than the attenuator, and certainly much easier to repair. So now the question is it this cable or is it this connector? It doesn't really matter. I'm going to have to take apart the entire piece, but at least we have something. And here's the little cable that connects the front panel to the attenuator, and this cable also measures just fine, which really only leaves us with one potential problem, and that is this front connector. I already started to remove it, so we can take it out and see what has happened to it and see if we can find a replacement. And here is the confirmation. This is really the only thing that is left, and yep, it does have the loss. Now interestingly, if I twist it, yeah, you can see I can change the, there you go, I just made a null inside of the response. Yeah, definitely something broken. We're gonna take it apart. Alright, so here's our connector, and although it looks reasonably okay on this side, it does not look good on this side. The centerpiece is certainly moved around, and I think it's somewhat free to move, and that's probably what one of the issues is. So it may be that remember this is an air dielectric connector because the frequency is so high. So this pin is suspended in between this ground coaxial connector via some holders that are around it. That's why it is so expensive, because these things are quite difficult to make with very high tolerances. So we're going to try and take it apart a little bit further to see if that rod is broken or not. Either way, this is not something that's so easily repairable, but at least we get to see what's on the inside. Oh yes, Pooch is super interested to see how this is going to play out. So let me see here. I loosened a bit. There we go. You should be able to remove it. Okay, so there's the rod. Oh yeah, that's it. Look at that. You know, that I look at it, it may not be so difficult to maybe fix it. That is actually shorting things out. That explains the attenuation. So we basically have a superfluous piece of metal that is a washer that's between this and that, and it's become dislodged, probably over time, because of many repeated connections and disconnection to this port. This is why often there are sacrificial connectors added to the outputs of these when you cannot remove the connector from the instrument anymore, so that if anything goes wrong, it happens to the sacrificial connector and not to the instrument's front panel connector. Let me see if I can remove whatever it is that is in here. Grab it, that is. It's difficult to work behind the camera. There we go. I got that piece. There it is. Those are the two washers that used to be there. In fact, this one is totally broken, and this one is now completely bent out of shape. But looking at this actually doesn't look too bad otherwise. It's even quite well centered. I'm not so sure what's holding this in place now. There we go. Okay, so this is not bad. No, this piece is good. All right, I'm happy with this one. And in the inside, oh, there's another washer there. Wow, there's so many pieces to this, huh? Okay, this one is okay. We can leave that spacer there. So I flattened one of those as much as I could. These are very, very fine spacers. Now, without the last one, if I put this back together, it probably doesn't make much of a difference at the frequencies we're looking at, especially because this connector doesn't need to be metrology grade. But nonetheless, we're going to measure its return loss, and we're going to measure its phase response just to make sure that it is good. So I'll just reassemble it based on these two washers, and we can give it a try. And there we go. And I think it looks quite a bit better. You can see right through the middle of the air gap, and on the other side as well. So it looks good. All right, here we go. We're measuring it again directly through the network analyzer, and there's the response. This is 0.2 dB per division vertically. I think it looks perfectly fine. So I would say that that works just fine in this instrument. This instrument probably hasn't been calibrated in a very long time anyway, but let's put it back together. Okay, so everything's back together. The oven is cold on there. You can see on the display. That's normal. I just turned the instrument back on. Let's give it a try. 1 gigahertz 0 dBm, and ta-da, looks good. What do we have here? Minus 0.59 dBm, which is about correct, given that we have a cable and connector and so on in the way, so that's pretty good. Let's go ahead and increase the frequency, just making sure this works. 2 gigahertz, 3, 4, 5, 6, and all the way until the end. And at 20 gigahertz, we're catching minus 2.24 dBm, which is still pretty good. It works. And then we can give it a try for a couple of different amplitudes. Of course, it's going to work no problem. Here is 10 dBm. And we can go all the way down, making sure the attenuators work. Here's minus 20. Of course, the attenuator works. Now we know that there was no problem with it. Here's minus 50 dBm and minus 60 dBm. Yeah, very good. Excellent. So right now, the spectrum analyzer has a 20 dB reference. So there's a big attenuation in the front. That's why you see it this way. Of course, if I change this one down to minus 10, you can see we get a much more stable measurement, and it looks pretty good. Yeah, really happy with it. But now that we did this, at least we should try maybe an experiment using the built-in modulation of this instrument. Let's do some constellations. So I went ahead and I connected to the wideband IQ inputs in the back of the instrument, connected my E8267D directly to it. So I was just about to run that test, and unfortunately I found out that this instrument, even though it has the connectors, the option is actually not enabled. But it does have the full internal IQ generator built in. We can always use that one. It's just that it's not as wideband as the rear inputs. Nonetheless, we can still do a difficult test, like a multi-tone test on it. So I have gone ahead and configured the IQ generator already. And since this instrument does have I and Q separately, it can apply a 90-degree phase shift between them and produce an image rejected signal. So you can place your tones in the upper sideband or lower sideband depending on how you configure the instrument. And this is why it can do, of course, IQ complex modulation and produce constellations of your choice. So I've put as many tones as I can right now within the bandwidth. I'm going to go and enable it. And there it is. It looks really messy, but it's actually not bad at all. Let's take a look over here. I'm going to zoom in a bit more so we can see more of the details. So first of all, you can see the up-converter phase noise both from the IQ generator as well as the synthesizer itself, of course. Here are all the tones, nice and equal amplitude. You can see that the LO has almost completely disappeared because it is supposed to do LO rejection. And there is a routine inside the instrument that you can run, and it will do IQ calibration for you. You have to run it every once in a while, and it will figure out if there is LO leakage, it will figure out if there is poor image rejection, and it will correct all of that. It's also like a diagnostics. It tells you if everything is working well, and the unit passes that test. And at the same time, you can see a whole bunch of IQ intermodulation terms that are appearing at the RF side, as well as the images of these tones. And the images are quite low. You can see they're below minus 60, while the amplitude is like minus 15 or so. So it's really quite good in terms of image rejection. Is as good as you're going to get, essentially. And there are some of these additional tones are the intermodulation nonlinearities of the SM200C as well. That's just from the Signal Hound's spectrum analyzer. But I tried this at different frequencies, and it works really quite well. So I'm happy with it, and I think the instrument is essentially back to normal. It may need a complete testing to figure out if there is anything else wrong with it, but I say it's a pretty good, successful, and simple repair. And there you have it. This was a fairly straightforward repair. Of course, you can't predict what repairs are like before you start working on an instrument, but there's a few more to work on. I have quite a few interesting instruments from AllTest still waiting to be repaired. So let me know what you think in the comment section, and I'll see you next time.